This is a Math 2 lesson summary video for the lesson titled Freddy Revisited. The purpose of this task is for students to examine independence of two events using two-way tables, and this is a solidify understanding task. In an earlier task, Terrell helped Freddy determine the amount of food and type Freddy should prepare for each day of his restaurant. As a result, Freddy's food waste decreased dramatically. As time went by, Freddy noticed that another factor he needed to consider was the day of the week. He noticed that he was over-preparing during the week and sometimes under-preparing on the weekend. Terrell and Freddy worked together and started collecting data to find the average number of orders he received of chicken and fish on a weekday and compared it to the average number of orders he received of each on the weekend. After 2 months, they had enough information to create the two-way table below. So when I look at this table, I notice immediately that there were less orders of both fish and chicken on the weekday when compared to the weekend. So what I wonder is the probability of someone choosing fish different on the weekday when compared to the weekend? Let's take a closer look to find out. What I'm going to do is I want to calculate the probability of someone selecting fish and compare that to the probability of someone selecting fish given that it was a weekday. So I wonder if these two would be different. Is it more likely for someone to choose fish anytime or to choose fish during a weekday? So to calculate the probability of someone choosing fish, we take this 153 for the total amount of fish orders and divide that by the total number of orders, and we'll get 0.45. To find the probability that someone would order fish given that it's a weekday, we are going to hide all of the weekend information. So I'm only looking at the weekday row. And there are 65 of the 144 orders on a weekday to give me a probability of 0.45. So it looks like the probability of someone ordering fish at any time is the exact same as the probability of someone ordering fish given that it's a weekday. That means that since these probabilities are the same, these events are independent. The day of the week does not affect the probability of someone ordering fish. So events F and D are independent. So to check for independence, algebraically, we can calculate the probability of event A and compare that to the probability of event A given event B. If these two probabilities are equal to each other, then we know that the two events are independent, meaning that one event does not affect the other. Let's take a look at another example. Let's compare the probability of chicken to the probability of someone ordering chicken given that it's a weekend. What we're checking is to see if the day of the week affects the probability that someone will order chicken. So to get the probability of ordering chicken, we have 186 chicken orders out of 339 total orders, giving us the probability of 0.55. To get the probability of chicken given that it is a weekend, we will only look at the data from the weekend. There are 107 chicken orders out of 195 total weekend orders, giving us a probability of 0.55. So we know that events C and E are independent, so the day of the week does not affect the probability of ordering chicken. Another way to check for independent events is to check out the probability of A and B and see if it's the same thing as the probability of A times the probability of B. So we already know that events C and E are independent. So let's find these two probabilities. I have here listed the probability of C and E, and this also means the probability of C and E. I just used the notation for the intersection. So if we look at our table, we can see that the probability of chicken and the weekend is 107 over 339, which gives us 0.3156. Now let's see if that's the same as the probability of A times the probability of B. So the probability of A will be the probability of chicken, probability C. So that is 186 over 339. The probability of B, or E for weekend, would be 195 over 339. When I multiply those two values, I again get 0.3156. These two probabilities are the same, again confirming that I have independent events. So in summary, independent events, when one event does not affect the other. You can check by seeing if the probability of A equals the probability of A given B. You could also check to see if the probability of B equals the probability of B given A. And then the other method would be to see if the probability of A and B equals the probability of A times the probability of B. All right, that's it for this video. Thank you for watching.